Okay, and our second speaker is Mozhdeh, who's going to be talking about metal rolling. So,
Yeah.
Thank you.
Hello, everyone. No need to say my name is Mozhdeh. I'm a second year PhD student. Today, I'm going to talk about a mathematical model for an industrial process in metal industry called rolling. My supervisor is at Ramley, and I also have some collaborators from Limerick University. So if you don't know what rolling is, Tom here actually illustrates this very well. So the strip of metals enters between two rotating rollers, and since the distance between two rotating rollers is smaller than the initial thickness of the strip, therefore the strip is squeezed out and the thickness reduces. Here we have a more proper version of rolling, and it's basically the same thing. And most of the time we need to repeat this process several times in order to actually get the desired final dimension, get the thin sheet metal. So I'm not gonna talk a lot about the microstructure, but still it's useful to see how rolling affects material properties and also some of the applications. So each tiny unit that you can see here is a single crystal, but referred to as a grain in engineering, and you can see that they are randomly oriented. After passing between two rotating rollers, the grains are elongated and they're all aligned with the direction of rolling. So this resulting sheet here is very hard to deform, and therefore it's ideal for application where no formability is needed, such as metallic appliances and also structural panel. But if more formability is needed, for example, in different part of cars, then we need to go through the sheet needs to go through subsequent heat treatment in order to recover its formability. So all I wanted to say is that the rolling is not only useful for manufacturing sheet metal, but also it has enormous effect on material properties. So the truth is that this process is very old, with one of the earliest drawing from Leonardo da Vinci, and then with the invention of electric power, it started to resemble its modern counterpart. But still, it's old with very little innovation. It continues to do what it's always done. For example, we don't know how to control the hardness that I explained in the previous slide, and also the curvature and the residual stresses. Therefore, the goal for doing this project is technology upgrade to the rolling mill, for example, in terms of having a control model that we can feed the rolling parameter and see its effect on the material properties, and also having a very fast model in order to use it in online process control. And the bigger goal is setting a foundation for actually modeling of different metal forming processes and not only rolling. And basically we chose rolling because it was the simplest one. So in order to construct a model for this process, we need to know how metals behave under the force. So if you go to WMG or other different places where material testing, you can find them spending lots of time on plotting curves like this. So this is stress-strain curve, stress versus strain. I should have used pointer. Yes, stress versus strain. And basically the idea is if you have a piece of material, it can be a piece of chalk, it can be rubber, or in our case, it can be metal. If you cut it piece of material and then put it in a specific machinery and then pull it apart, pull it out, you can attach a tiny sensor here and then record force and deformation. So is it not completely free screen? Yeah, never mind. So the stress basically is force per unit area, and strain is deformation per unit length, and basically it is force per deformation curve. So it has two specific areas, elastic area and plastic, and basically elastic area is the area where the relationship between stress and strain is linear. So if you stretch a material up to somewhere in this pink region and then release the force, you basically come back to the origin. So you recover all the deformation. But if you pull it hard enough and pass a specific point called yield point, then the deformation is permanent, and you can't recover the deformation by releasing the force. So these are two specific areas with their specific equations. And if you want to model metals correctly, you need to consider both of them. But the truth is that the elastic region is so smaller than, in metal, is so smaller than the plastic region. And therefore, in order to make the model simpler, we completely neglect the elastic part and therefore the elastic equations. So why not even make it simpler by considering a constant force instead of varying force? And now this material model is called perfect plasticity, and this is what we use the equation of it in the model. Now, getting into the equation for the geometry, this is the schematic of rolling. Again, sheet enters from the left between rollers and comes out thinner from the right. And actually, we are interested in the rolling gap, the area which is confined between these two black lines. And everything before and after it is not important for us. If you zoom in into a material point, you can see that the material experiences normal stresses and also shear stress. Normal stresses sigma xx and sigma yy as a result of the fact that the sheet is actually under the force and also is stretched, and the shear stress because of the friction. So we have three unknowns and we need three equations. Two of them come from conservation of momentum with zero inertia. Basically, we consider that the speed of sheet is almost constant, and the system is closed by the yield criterion, which basically says in what combination of stresses plastic deformation begins. And kappa here is constant based on the assumption of constant force. And on a surface, we have slipping friction, which model it with Coulomb friction. And this basically means that tangential force is proportional to normal force, and mu is the coefficient of friction. We also need another set of equations to actually convert stresses into strains, but I just didn't put them here. And we need, so we can solve this equation. These are all equations we need for the stresses. We can solve it, for example, numerically with the finite element, for example, simulation softwares off the shelf. And the problem is that they are very slow. It takes very long in order to find a solution. And we are looking for a solution which is so much quicker. So the first step to get the analytical solution is non-dimensionalizing the parameters. So we scale all the lengths with initial half thickness h0, and therefore, for example, x is equal to 0 at the entrance, and x is equal to L hat over h0 hat at the exit. And also, we non-dimensionalize all the stresses with kappa, which was the amount of yield stress. And we also introduce delta, the ratio of initial half thickness to the length of roll gap to be so much smaller than 1. And this is actually the second handle we use in order to make the equation simpler and find the solution analytically. So delta is so much smaller than 1, and also we assume that mu is smaller, mu is small, and therefore we are able to scale it with delta. Now you can see that all the equations with hat in a previous slide are now without hat, which means that they are non-dimensionalized. And also we had delta in the equations, which is a small, and therefore we can use asymptotic analysis to find a solution. So it basically says that, so you can find a solution by neglecting the small terms in a leading order and then reintroduce small terms in order to find the corrections to the solution of the leading order. So in the process of solving the equation, we decided to actually change the variable and use the potential function. We use the area stress potential function. And the advantage is that we now can define all the components of stresses based on only phi. And also these definitions satisfy the force balance. So not only we left with less number of parameters, but less number of equations. And now we have the yield criterion subject to this boundary condition. And the purpose is finding the solution for phi. So in asymptotic analysis, the choice of a scale is very important. different choices of scales may lead to different solutions, and not all of them are correct. Here we have two different scales. One of them is H0, which is small, and the other one is L hat, which based on this assumption is so much H0. So if we use H0, we can see the rapid changes in a solution, but on the other hand, we are not able to see how solution varies over the length of L. And the choice of L actually provides opposite advantages. For example, in one of the latest asymptotic model for the rolling in a literature, Minton, actually the author, used L hat in order to scale the parameters with, and therefore he wasn't able to see the rapid changes in a solution. So I hope with this description, you are convinced that we need to use both of them in a method called multiple scale asymptotic. So we introduce new parameter Z, which is a scale with L hat, and therefore Z is 0 at the entrance, and Z is 1 L hat over L hat at the exit. And instead of X, which actually non-dimensionals with H hat, and I've already used it in a previous slide, we use N. N and X are both of them a fast variable, but it turned out that the use of N is more useful in seeing the results. So just to see how they're going to use in equation. So in a previous slide, we have d by dx and also d squared by dx squared. And now we can actually use simply chain rule in order to actually write x in terms of new parameters. And then we need to find a solution for phi in asymptotic expansion, which is basically a power series. And the corrections are in terms of delta. For example, phi 1 is a first order correction, phi 2 is second order correction, and so on. So these are the solution to the equations. I'm sorry that they're very unpleasant to look, but it basically says that phi minus 2, phi minus 1, and phi 0 are all the leading order solutions, and we are able to get the leading order pressure, while phi 1 is a first order correction to the solution. And we have actually the hyperbolic equation for phi 1, and the solution is in terms of a wave. So this is a general solution for wave, and we need to actually find the A. We need to find the N, Y, and Z dependency for A. So in order to find the Z dependency, we need to go to the next and therefore get the evolutionary equation for A double prime. And in order to get the N and Y dependency, we basically need to use the initial boundary condition at the start of roll gap. And this is how this solution looks like in XY plane. So let me explain what you are looking at. So the top row is a pressure distribution and the bottom row is shear stress distribution. Again, the sheet enters to the roll gap from the left, goes between two white rollers, and then exit from the right. So we have the leading order solution, the leading order from plus a first order correction, and finally finite element simulation to compare the results with. So you may notice that instead of leading order solution, I title it as a slab method. And the reason is that in a leading order, we basically get the homogeneous compression. And this is exactly what a classical method called a slab method assumes. So the pressure start of some value increase up to the neutral point. Oh, I forgot to explain the neutral point. Okay, so increase up to some point and then decrease from the neutral point outward. But in a multiple scale, and basically when we add the first order correction to the leading order, you can see that we have a wave on top of the solution. And this basically matches with the result from finite element simulation. Again, for pressure, that the direction of shear stress changes at a neutral point. This the point on the surface which the direction of shear changes is called neutral point. So it predicts that the direction of shear changes at a neutral point, which is completely fine, because the reason is that the change in the direction of actually friction force on the surface. But the problem is that it also predicts that the discontinuity runs through the thickness. So this is not correct, and this is only an artifact of slab method. While in the multiple scale, you can see that the direction of shear changes in a diagonal line, and it changes not only once, but many times. And again, it is inconsistent with the results from Finite Element. So here is another set of results. Again, you are looking at the shear stress distribution with multiple scale and Finite Element simulation. And you can see that the multiple scale is able to capture most of the trends in Finite Element. For example, it predicted the location of neutral point correctly. And also, if you count the number of waves here, you can see that it is inversely proportional to the delta. Delta is actually aspect ratio. And it is true, again, for the Finite Element. And I think the interesting takeout from this result is that although all of these are the same material with the same initial thickness, but you can see the intensity of shear stress is different, and this may affect the hardness of actually the sheet. So I'm not saying that this model can predict the hardening, but I'm saying that it seems that this oscillatory pattern may have a connection to it. Some other insights from the results. So what you're seeing on the top is a shear stress distribution, and I only show the half top of the sheet because it is a symmetric process. The top and bottom are the same. But if it is asymmetric, and then you can imagine that this pattern on the top and bottom would be different, and the way that these waves are located with respect to each other may affect curvature. That I said is one of unknown about this process. And the other unknown I said is residual stress, and residual stress is actually the stress that remains after the process. And you can see the location where the exit wave actually leave the roll gap can show the huge amount of residual stress. So again, all of these are hypotheses, but it seems this oscillatory pattern has linked to these kind of unknowns. And finally, conclusion and future works. We have a new model that in the leading order, it can recover the results from slab theory, but in a first order correction, it reveals a set of waves that actually varies over the short length scale of H0. And also the results were successful in predicting most of the trends in Finite Element model, while it requires less time. So for this model, it takes 2 seconds, while for the Finite Element, the shortest one, requires at least 15 minutes. And for the future work, as I said, we use perfect plasticity, and the first thing to do is to include elasticity and also hardening in the equations, and then this may affect the initial boundary condition. So if I go back to these equations, so I noted that the n and y dependency comes from the boundary condition, and we actually chose the simplest boundary condition to get the linear actually function for A. But if we include elasticity, then it wouldn't be linear, and then we need to solve this equation numerically. And the difficulty is that we have a discontinuity, we have a shock wave in a boundary condition, and therefore we need to carefully actually track the speed and also the amount of shock. Yeah, these are all I wanted to say, and thank you for listening. I would be happy to answer any questions.